All right, I'll go ahead and get started. Good morning, everyone. I'm Alejandro Companioni. I'm a junior software engineer at Knewton. I'm going to talk about Leptoid today. And more importantly, I'm going to talk about some lessons I learned about autoscaling and instrumentation while working on Leptoid. I'll go ahead and just answer the first question you might have right off the bat, which is like, what the hell is Leptoid, right? You might have looked at the schedule and said, what the hell does this mean? So Leptoid is actually a type of scale that's found on higher order types of fish. And these scales allow for increased water flow around the outside of the fish. And that reduces drag as the fish moves through the water. So this fish is pretty excited about being able to move through the water really quickly. So we were equally as excited to get our server capacity moving up and down pretty quickly and kind of like decreasing drag when it came to capacity planning decisions. And so, approaching this problem was interesting. I actually did not start working at Knewton in any type of capacity planning role. I was actually a data science intern this spring. And after I decided to stay aboard at Knewton as a junior engineer, I was given this really interesting problem, right? How can we take load data, whatever load we're experiencing at any given point in time, and try to forecast what future capacity we'd need based on whatever data we currently had at any given point in time. And I found this to be an interesting problem. And so, talking about interesting problems, I can go in one of two directions from here, right? I can pitch Knewton as a place where we work on really interesting problems and we have ping pong tables and espresso machines and you should totally come work for us, right? I could do that, but I'm not going to do that because it's kind of boring. I could also pitch you on Leptoid itself as a library that you guys should look into and say, it's like the most amazing library ever. It solves all your capacity planning problems. You should look into this and, if you go ahead and implement it in production, you can just kick up your feet and have a beer and just relax while everything scales up and down. And I'm not going to do that either. I actually open source Leptoid as more of a case study in terms of researching an autoscaling problem and trying to improve what we know at Knewton about capacity planning in the hopes that maybe every one of you could learn something from some of my experiences. And so I actually find these experiences to be more important than any of the code I've actually written. And so from there, you need to actually think about attacking the problem, right? And so given my research background, you start by trying to robustly define the problem. And so what do you need to autoscale, right? That's like the first approach you need to take. You have this problem, you need to define it well, and there are some premises that underlie the problem. Some things that are assumed about the problem before you can actually start attacking it, right? So you need a couple of things to actually autoscale, at least in my opinion. And you may agree or disagree, and I'd love to hear what you guys think, but I think that you need 4 things to autoscale, right? First, you need a model, right? I'm not talking about Blue Steel Zoolander model, obviously, but I'm talking about a mathematical model, something that can take whatever load data you're experiencing at any given point in time, and try to correlate that or identify some relationship between maybe historical load data, or maybe some I/O load that you're experiencing on your server, or on your database, or something like that. But you do need some kind of mathematical model to describe this relationship, right? So in addition, you also need some kind of motivation, right? So you could be like this 1990s era infomercial superstar and just talk about free money being your motivation, right? And go apply for government grants and wear really cool question mark outfits all the time and stuff. And that's totally noble. That's totally fine. If you want to optimize for money, you just pick an objective function. In this case, the objective function you're trying to optimize for is decreasing the money you spend on your capacity. That makes perfect sense, right? Alternatively, maybe you're focused on improving customer experience, and so you want to decrease round-trip response time, and maybe you want to make sure your 95th percentile responses are as low as possible. That's also good, but you need some kind of criteria that you want to work towards while you're trying to autoscale. In addition, you also need tools. You need the right tools in order to autoscale. So when I'm talking about tools, I mean things like continuous integration, one-step deployment, or one-button deployment. I feel like this is pretty old hat. This is stuff that all of you should probably be doing. I don't have that much experience. It's all I know as an engineer, and so I figured it's what pretty much everybody else should be doing. In addition, when it comes to tools, I'm also assuming that you have some kind of cloud-based infrastructure, maybe something on EC2 based on AWS, where you can actually increase or decrease server capacity easily. I'm not sure if this may necessarily apply to co-location. Maybe you have some private cloud that you operate on, and in that case, maybe some of these lessons will apply to you. but that's what I'm referring to when I'm talking about tools. And so those are 3 of the 4 things. I think all of these things completely pale in comparison to actually having data, right? So if you don't have data and you try to auto-scale, it's going to be a miserable experience, right? Like, it's just not going to go well for you at all. And so if you don't have any data and you're not instrumenting your code properly, you're not going to know what to do once it comes time to plan your capacity or anything like that. And so this is actually similar to my experience so far in research, where you'll hear data scientists and other people say all the time things like, I spend so much time cleaning my data, getting it into like this form that I can analyze easily. That's like 75, 90% of my work or something like that. And actually Ted Juba, a person who's pretty opinionated admittedly, had actually a really good blog post about this not too long ago, where he talked about how easy it is to actually produce amazingly novel or interesting research when you have clean data. So like you could take like this perceptron classifier, apply it to like a Reuters text corpus, and just try to classify maybe text sentiment or something like that. And that's easy. That's like really, really easy, because if you're like working at an academic institution, all you gotta do is pick up the phone, you call Reuters, and you ask them for a data set. Maybe you gotta go back and forth, or maybe you hire a grad student to do it for you. But you get this really, really nice data set. You can just dump it to any database you want, you can just analyze it easily. But that's usually not reality. You can't call the server load gods and just ask them for the cleanest data imaginable, right? You'd actually have to go about cleaning that on your own. And so like when I initially had this problem, I approached it kind of naively. I was like pumped. I was like ready to develop this like super amazing model, something that could just run 24/7, scale everything up and down, just like abstract away any problems I had about like planning capacity at Knewton. I could publish tons of papers about this, and it'd be super interesting work. But actually, as I worked on this problem more and more, I started finding out that the models were way less important than the form your data is in, how you're storing your data, how clean it is, and how easily you can access it, right? And so, in fact, I think this specific problem, this specific concern, that of data over modeling, over deployment, over tools, I think it's so important. It's basically what I'm going to focus on today. And so what am I going to actually skip? I'm not going to talk about any of these things up here, the other 3 pieces that I mentioned earlier. So I'm not going to sit here and talk about whether you should use a polynomial kernel or a radial basis function kernel or something in your support vector machines to try to analyze your load. I'm not going to go into any of that. I'm studying machine learning and statistics right now, and so I'd be happy to discuss this with you after the talk. But I think, again, the lessons I've learned about instrumenting and data are much more important than what model you use, and I'll go into that a little bit later. And so in addition, I'm not going to talk about deployments or deployment systems or continuous integration or any of that. I feel like probably everybody else in this room can come up here and give a better talk on deployment than I could. So I'll just let you guys think about that and think about how to best solve that problem in your situations. And then similarly, I'm also not going to talk about designing your system so it's easily scaled, right? I'm not going to talk about adding or removing nodes from your Cassandra cluster or anything like that. I'm not going to talk about writing your services so that they're horizontally scalable. I'm not going to talk about any of that because, again, you guys could probably talk more about designing systems than I could. Instead, I'm going to go ahead and focus on this data and instrumentation problem because I think it's the best value I can add for you guys today. Okay, so I want to apologize. I'm sorry. I just lied to you. We built a little bit of report, and I'm going to completely break it right now. It's because I said I wasn't going to talk about models. I am going to talk about a model for 1 second, but it's going to be the model that we used, just because the model that we actually chose ends up kind of informing what data we need, right? And so I invite you to join me as we go to like a happy, wonderful place. We're going to go to the post office, and you're going to have a ticket in your hand to go pick up a package that you might have missed one day while you were at work or something like that, right? So you're wearing your white shirt. You're going in during your lunch hour, and you stand in line with the other people wearing white shirts up there, and you have your package pickup ticket, right? And you're holding on to that, and you're waiting to speak to one of the postal clerks in blue. And those postal clerks, they can pretty much help you with any other type of need you may have, but they can't help you with package pickup. You'll actually need to go talk to the manager, who's wearing the spiffy red shirt down there, if you want to actually pick up a package. That's because the manager has to check your ID or something like that. There's only one problem with this scenario, and it's that the manager's really lazy. The manager's so damn lazy, especially when lunch rolls around, that there's not going to be any package pickups happening at this point, right? Manager's just thinking about what kind of sloppy burger he can eat, or whether he wants like a Philly cheesesteak or 2 Philly cheesesteaks. He can't decide, right? And so if you roll in during the lunch hour, you're going to have a particularly long wait while you're waiting to pick up your package. In fact, it's going to get so long that you're going to end up just like standing outside of the door waiting for the package to show up, right? That's because the manager, as lunch hour rolls around, he's doing a really poor job clearing out the customers that are in queue waiting to pick up their packages. Little by little, as time goes on, his queue starts to back up, and as a result, the clerks at the top, their queues start to back up as well. And so you have people like filing out the door at the post office, waiting to pick up their package, all because the manager can't wait to go and get a bite to eat, right? And so this is actually a solved problem, fortunately. Maybe not the whole post office waiting in line scenario because it still sucks and there's no way around it, right? But a gentleman by the name of Erlang actually solved this problem in the early 1900s. He was analyzing the Danish telephone exchanges, and his research formed the basis of a field of research. His research formed the basis of a field known as queuing theory. Queuing theory is basically the study of how stable or unstable a queue has become, and it's used to analyze any number of things. It's used to analyze telephone conversations coming into an exchange. It's used to analyze people waiting at a post office. It's used to analyze people waiting at a bank. It could also be used to analyze requests coming into your systems. There's a key idea in queuing theory known as utilization. Utilization is a description of how stable or unstable the queue has become at any given point in time. It's a function of the rate at which requests are coming in divided by the rate at which those requests are being serviced, right? And so this makes conceptual sense when you think about it, right? So let's say you have 100 requests coming in per minute, but you're able to service them at a rate of 150 requests per minute. Well, that means you have more requests being handled, being serviced at any given point in time than you do coming in. And so this ratio ends up being less than 1. And that's actually a good thing, right? That means you have a stable queue. As requests in queue, as they join up in this queue, you're going to process them efficiently and quickly, and you won't get backed up in this queue. Conversely, if your arrival rate's higher than your service rate, that means you're not handling requests as quickly as they're arriving, right? In the alternate example of the numbers I just gave, maybe you have a request arriving at 150 per minute, and you're only processing them at 100 per minute. I mean, this makes intuitive sense. Soon that queue is going to have 50 extra requests, then 100, then 150, so on and so forth, and the queue is just going to become completely unstable, and you won't be able to process any of them. And in this scenario, utilization is greater than 1, and that's used to describe the instability of a queue. Specifically, the idea that the queue has become too unstable and you're no longer processing requests efficiently. So I took you down this queuing theory hole for a second or two. And so why did I do that? Well, it's because queuing theory applies really well to the way we've designed our systems at Knewton. So at the highest level, requests coming in approach an initial level of application Nginx proxies, and those requests can get routed by the proxies in the initial Nginx proxy layer in one of two ways. They can get sent to any of our applications, like Noodle or Numina or our course apps, or they can get rerouted down to a secondary layer of Nginx proxies for our web services. And by web services, I'm talking about our recommendation system, I'm talking about our authentication service, our schedule service, study service, so on and so forth. And so this is actually really, really convenient for the purposes of instrumenting and trying to plan capacity, right? Because if you think about it, every single request actually has to go through one Nginx proxy, right? And so actually trying to extract data from this scheme is really, really easy. It's as simple as just instrumenting the Nginx proxies, right? And so like I discussed earlier, if we want to try to identify utilization, and say there's like a hypothetical queue in front of each of our applications or each of our web services, we can actually instrument the Nginx proxies via scraping their logs. And then from there, we can understand both service times, in other words, how long it takes to satisfy a request, and arrival rates. It's worth pointing out that you can simply add a configuration in Nginx so that you can track the amount of time it took to satisfy one single request, and you can have that log. That's really straightforward. And so this is actually really nice. Once we change that one configuration in Nginx, we have every single request. For every single request, we have information about how long it took to service that request. This is great news, right? That's 1/2 of the utilization component I just talked about earlier. And so in addition to that, we also just by virtue of every single request being logged as it arrives at the Nginx proxy, we also have information about arrival rates. And so, you could think about this from a MapReduce standpoint. It's as simple as just taking every single entry in the log, reducing them all, and just saying we have 20 requests arriving for example, our recommendation service over the last minute, just for example. And so this is super convenient, right? Because now we have all the data we need, as I described earlier. We have service time and arrival rate. Well, actually, it's not exactly right? Because as I described utilization earlier, it's actually a ratio of arrival rate to service rate. I mean, obviously, you could take the inverse of the service rate, and that's just a service time. So by taking the product of the arrival rate and the service time, we can actually just measure utilization on a server-by-server basis. That's actually a key point here. I want to point out that utilization, as it's been defined, is for an MM1 queue setup. In other words, a setup that has a single queue. And I'll actually address that a little later as well. But this is great, right? This is awesome. We have all the information we need to try to measure utilization on a server-by-server basis. We have the arrival rates we need. We have the service times we need. And now we have data. So what do we do with it? I mean, how should we actually analyze this data? Well, this is the part where you want to have the model that you picked out earlier. You want to use that model to try to describe the data and use that model to forecast into the future as well. And so wait a minute, though. I lied again. I'm sorry. I'm going to talk about picking a model a little bit. But I think this is also super useful because you could take our lessons in picking a model and apply them to your situation. And so in our case, we performed a little bit of exploratory data analysis. Oops. In our case, we performed a little bit of exploratory data analysis, but when it came to picking a model. But remember that we're an education company, and so it's easy to kind of just look at my own experience, try to think about what I did as a student in order to think about an appropriate model, right? So as a student, I didn't study at all during the weekends. And so similarly, you can imagine that we'd experience less load over the weekends, maybe Saturday and Sunday. Within any given week, within any given week, Saturday and Sunday, we'd experience less load. As the semester went on, all those Saturdays and Sundays of not studying would probably catch up to me, right? And so I'd actually start to study more and more during the week as finals approached. I'd start getting a little more nervous and anxious about it. And so you can imagine that on our end, on Knewton's end, we'd actually experience more load. We'd experience an upward trend in load as the semester would go on from a student behavioral standpoint. Then in addition, once school is out, nobody's logging on, right? I mean, you're not cracking your books open the day after finals. You're off hanging out, partying. I know I did. And so similarly, we'd expect nobody or very, very few people to actually be on our systems at any given point in time once the semester is out. And so I've described this type of weekend-to-weekend behavior. I've also described this beginning versus end of semester behavior, and I've also described this in-school versus out-of-school behavior. And this all lends itself to a time series model, right? Specifically one where we can decompose all these pieces into seasonal, trend, and cyclical components, where whether school is in session or out of session would represent kind of like an irregular cycle, similar to like an economic cycle, like a boom and bust period. The Saturday and Sunday behavior is actually pretty consistent. It has like this consistent periodicity. It occurs consistently every single week while school is in session, so we can call that a seasonal component. And that's similar to like consumers spending money towards the end of a year as the holidays roll around. And then there's also this upward trend component that I described, which is, towards as the semester moves on and finals begin to approach, more and more people actually start to log on. And that's similar to how just the economy grows at any given point in time. And so I actually performed a little bit of exploratory data analysis to try to think about this. And so just by looking at this chart, you can actually confirm some of the things I just hypothesized right now, to a certain degree anyway, right? So this chart shows data for every single week in the year 2012 up until about mid-September, so I think it was last week or so. These are all overlaid onto each other such that every single line on this chart represents a single week starting from 12 a.m. on Sunday, or actually it's 8 p.m. on Sunday, moving forward until 7:59 p.m. Later on Saturday that week. And all these lines are stacked upon one another. And the goal here is to show density with respect to user activity on our systems. And this kind of confirms a couple of things, right? So it confirms that behavior that I was talking about with respect to certain days of the week having less student activity than other days of the week. So that's good. I was a little off about when that would happen. It seems that it happens on Sunday and Monday instead of Saturday and Sunday, but that's still good. There is some consistent periodicity with respect to how students are active on our systems. In addition, we've got these incredible troughs of user activity during the middle of the night. And that makes intuitive sense, right? Nobody's going to be studying at 4 or 5 in the morning. And so you see user activity completely drop off. But there's actually an interesting component to this graph, and that is the steepness with which user activity picks up so quickly after these troughs. And so you can take a look at, for example, the Wednesday peak, actually the Wednesday trough. So you can see right between 8 p.m. and 8 a.m., Tuesday night / Wednesday morning, how deep the trough is. And you can also see that it picks up very, very quickly, ramping up to arguably our highest levels towards around noon or 1 in the afternoon on Wednesday. And so that's actually a really interesting feature of our data in that when load actually arrives on our system during the semester, it actually arrives at a very, very high rate. There's like a high load acceleration, and that's an interesting thing to handle when it comes to capacity planning. And yeah, another thing to address as well is the variance in peak magnitude as well, right? So you can see, for example, our lowest peaks, in other words, Sunday night, or rather Sunday afternoon, are 1/3 as high as Wednesday peaks. In other words, the highest of the highs that we experience during the middle of the week are much, much higher, 3 times as high as any peak we experience on the weekend. So there's also a lot of volatility with respect to the highest load we experience in any given day. And you can actually see this whether it's Monday, Tuesday, Wednesday, or rather Tuesday, Wednesday, Thursday, or Friday. They all have much higher peaks relative to the off days, Sunday and Monday, right? So these are also good to know when it comes to choosing a model, or validating our model in this case. So in addition, I also wanted to confirm this idea about student behavior towards the very end of the semester, right during finals, and then right after finals as well. And you can actually confirm this by looking at this chart. So the light blue line actually represents student activity the week before finals at this given partner school. And the red line is the following week, which is actually finals week at this school. And you actually see a drop-off after Wednesday night. And that's really interesting because this is for the spring 2012 semester. And I actually went and I looked at the academic calendar for the school. I just wanted to confirm this. And it turns out that Wednesday was actually the last day of finals at this school for this specific week that I'm plotting. And so this confirms our intuition, right? Thursday, the following day, we see almost no load on our systems as a result of finals ending. And that's great. That makes sense. That's a little bit more validation for our model. And that behavior continues through the rest of finals week, post-finals concluding. And then moving into the next week, the dark blue line all the way at the bottom, you also see almost no load. And that's great because that's the first full week out of school after the spring 2012 semester, and we don't see any load. And so, this is, okay, all right, so you can take kind of sort of a cynical approach to it and say, okay, well, obviously, students are not going to log on when the semester ends. But, and I would agree with you. I wouldn't deny that for a second, right? But, so let's go back to this chart for a second. So remember that I pointed out that the volatility in magnitude, the volatility in peak magnitude between Wednesdays and Sundays, right? There's very, very, very high amount of variance between those two. So what happens if you're not capacity planning at this point? Well, you're hanging out at the office, working on a library, maybe writing a new chef recipe or something, and then all of a sudden Wednesday afternoon rolls around, you get that highest peak of user activity rolling in, and all of a sudden everything starts to fall over. Your writes to your database are backing up or whatever, and things are just really, really slowing down. So what you do if you're not doing proper capacity planning is you'll just go ahead and provision tons and tons of servers. You're just going to get on AWS, you're just going to jump on the EC2 command line tools and just add instance, add instance, add instance. And what you're actually going to end up with is just like an aircraft carrier of instances, right? You're just going to have like tons and tons of elastic compute instances floating around. And that's not really too helpful, right? So this behavior that I talked about earlier, yeah, it might make intuitive sense, and it might seem obvious in retrospect, but you need to confirm it, because if not, this is what your system looks like. It's just a humongous aircraft carrier of hosts floating around. And at that point, you're not really capacity planning. You're just throwing money at the problem, and that's not the efficient way to try to solve the problem. So anyway, enough about that tangent, right? And so now we've got this model in hand. We've validated it using a little bit of exploratory analysis. And so what should we do with the model? Well, we need to think about how we're going to use that model to represent data in memory as part of our autoscaling library. And so in my specific case with Leptoid, I actually use Python in some of its scientific computing libraries because that's what I'm most familiar with, right? And there are a couple of really, really nice libraries in Python to help with this problem. There's NumPy. NumPy is based in native code, and it has multi-dimensional data structures that are super easy to use. They have fancy indexing. They're based in native code, so they're extra fast. And so representing multi-dimensional data, very, very easy with NumPy. Since I was talking about time series analysis earlier, a library like Pandas would actually help out with that. Pandas has a great time series data structure where in addition to the normal fancy indexing you get with NumPy, you also get this fancy date-based indexing with Pandas, where you can say, for example, give me all the data between September 24th and September 27th. And you can just index into Pandas using those date-time objects in Python, and it'll give you all that data. Super convenient. And then maybe you want to specify a model in native code because writing something in C or C++ is going to be faster than writing a model in Python or Ruby or anything else. And so Python actually has Cython, which will let you interface with this model that you've written in C or C++ very easily. All you have to do is compile it, and then with Cython, you can just import it into your autoscaling library written in Python, and now you have access to a model written in native code that just runs super fast. So in addition, I also defined some data structures in Leptoid because you can have all the data in the world, but you actually need some additional metadata information grouped with that data while you're performing your analyses. So I defined this service queue object that in addition to collecting the arrival rates and the service times for each instance that we were analyzing, it also collects data about the EC2 instance itself, its instance ID, the service that's being hosted on it, whether it's our recommendation service or our authentication service or anything like that, and what environment it exists in, whether it exists in our staging environment or our production environment or anything like that. And so there's one problem with picking Python, which is the fact that there's actually no good time series forecasting library in Python right now. Stats models is pretty good, but as I talked about the cyclical and trend and seasonal decomposition stuff earlier, you can't really get that out of stats models just yet. They're working on multiplicative decomposition right now, but it doesn't exist. So what we actually had to do with Leptoid is specify a model in R and then bridge into that using RPy2. And it works. You can specify the model in about 5 or 10 lines of code. But it's hackish, right? There's this library in the way. RPy2 is not well maintained, so maybe one day it just ends up, one day we move forward to Python 3 maybe, and then compatibility breaks with RPy2. All of a sudden, we don't have access to our model. And so this is actually something very important when it comes to designing your autoscaling system. Excuse me. And that is that you need to make sure that your autoscaling system is actually modular, right? Let's say this scenario happens where we decide to move forward to Python 3. Or let's say that we decide to use stats models because they finally offer us some kind of multiplicative decomposition. Well, if you design your autoscaling library so that it's modular, you can actually just swap out the model, insert a new module, redefine a couple of methods, right? And then that's it. You're still producing a forecast. Whatever's coming out of this forecasting module is still a forecast of utilization. And so the piece that reports from the cloud, Graphite in our case, the piece that reports from Graphite into our autoscaling library doesn't see anything different. And the piece that's responsible for making calls to our deployment system doesn't see anything different either. And all we have to do is swap the model in and out. And so actually that's like really convenient, right? Similarly, if we decide to change our deployment system, then we just swap out the piece that makes deployment calls, just insert a new piece, and then same thing happens as before. The forecast goes in, and then we just make deployment decisions based on that forecast, right? And so we're actually experiencing something like this at Knewton right now. We actually have a legacy product, and we have a new platform that we just rolled out with Pearson, one of our biggest partners. And this new platform that we just rolled out has a completely different deployment system from our legacy product. So if you didn't write a modular autoscaling library, you'd have this problem of having to rewrite a big chunk of the library. But in the case of Leptoid, we actually just have to replace something like 50 or 100 lines of code with calls out to this new deployment system. And in this scenario, we can actually run 2 different instances of Leptoid. We can actually run an autoscaling library in our legacy environment. We can actually run an autoscaling library in our new platform environment. And both of these libraries, both of these services can manage our capacity easily with very, very little development time. And that's actually a super convenient way to attack the autoscaling problem as long as your library is modular, right? Okay, great. So we've got everything we need, right? We've got all this data, and we've got all this modularity, and we even went meta. We talked about modularity, which means like we're really, really serious about this software development thing, right? And we can get cracking now because we've got utilization and we've got everything instrumented. We're ready to go, right? I mean, so not exactly. That's not necessarily the case. And this is actually the reason why I decided to talk about instrumentation and data instead of trying to pitch you on Leptoid or anything else. What happens if you don't have this convenient system design where you can just instrument the Nginx proxies? What do you do in that case? Well, maybe in that case, you actually go ahead and instrument your code using statsd, which has any number of libraries in tons of different languages like Python, obviously JS. I mean, you can just, it also provides all these great primitives for tracking how long it takes to call out to a method. You can actually count the number of calls and things like that. Shouldn't really have any questions when it comes to instrumenting code other than to use statsd. Except for, what if your code base is in Java, right? Well, you can actually use Codahail's metrics library, which is what we actually use at Knewton to instrument our new platform code. Codahail's metrics library admits a ton of really, really nice instrumentation primitives, just the way statsd does. Both of these actually transmit data to Graphite very, very easily, very conveniently. You just have to instantiate objects in Codahail's metrics library and just make sure the connection is set up properly, right? And so that ends up being really straightforward, at least when it comes to instrumentation. But the general idea here is that when it comes to instrumentation, there's not one single silver bullet or special solution that's going to work for everybody. So you need to think about this problem, right? So in addition, what about the scenario where you have like a junior engineer who just started at your education-based startup in New York, and he's responsible for managing your Graphite cluster, and the cluster just keeps falling over and over again, and it just, all the different hosts on it fail. This is hypothetically speaking. I don't know any junior engineers like this. But if I did, I would tell the head of systems at that company to be extremely patient while the junior engineer tried to figure out what the hell was going on. Eventually, the junior engineer might get around to thinking about what the problem was. He might end up working with some developers, and he might find that the problem actually ends up being a configuration issue on our new platform side, such that all our services are reporting to Graphite every second instead of every minute. So configuration management really sucks. But again, you have to be a little patient while you're trying to get this instrumentation stuff worked out. It's definitely not straightforward. The Graphite team has done a really good job of trying to make it very, very easy to set up a cluster, but depending on how junior your hypothetical engineer might be, you might run into a little bit of problem. And so there's actually the biggest problem. There's also another issue that you might run into when trying to develop some kind of autoscaling solution on your own, and that's the idea of pitching your boss on it. So great, we've talked about approaching this problem and how to think about this problem a little bit, but what if your boss is a little bit reluctant to let you write something like this? Well, you can pitch them on the idea, you can pitch your boss on the idea of the amount of money that you're going to save from having automated capacity planning solutions, right? And so I'll use Knewton once again as an example. We're testing Leptoid right now in our legacy staging environment. We're applying load to, we have our production environment mirrored in staging, and we're applying load, and we're trying to see what kind of scaling decisions Leptoid makes. Once those load tests are fine and everything works out and we're able to iron out any extra bugs we have with Leptoid, we'll go ahead and deploy it in our production environment. And once we deploy it in our legacy production environment, we're talking about saving thousands of dollars a month as long as that environment exists. And that legacy environment is just a portion of our total infrastructure. Eventually, we'll port Leptoid over to our new platform, and it'll be responsible for scaling our new platform hosts up and down. And there we're talking about thousands, if not tens of thousands of dollars saved every month. And that's something that any pointy-haired boss can agree with, right? You can just pitch the idea of saving money, and that should actually get you enough approval so that you can work on this problem. But so I talked about pitching your boss on this. I talked about instrumenting your code or maybe not instrumenting your code. I talked about the hypothetical junior engineer who may or may not break your graphite cluster, not that I know anybody like that. So all of these things serve to illustrate one single point, which is autoscaling is extremely ad hoc. Your solution probably only works for you. I know that our solution probably only works for us. And that's why Leptoid is actually open sourced as more of a case study for you guys to take a look at than anything that you might actually want to use. I think that the decisions we made with Leptoid reflect our decisions about system design, about deployment, more than anything else. And I don't know how helpful that might be to you beyond this idea of how important instrumentation and data are, right? If you want to try to autoscale, you need to have your instrumentation system in order, or your instrumentation protocol in order. You need to have all of your data in order. You need to be able to access that data easily. Otherwise, you won't be able to autoscale to begin with. So if there's one thing you take away from this, it's that you need to make sure you have your instrumentation squared away, and you need to make sure that the data produced by that instrumentation, when it comes to autoscaling, is such that it's easily accessible and easily analyzed. Otherwise, there's no hope for actually autoscaling. And so I'm actually going to go ahead and show you some of the things that we've done as a result of working on Leptoid. And first, I want to thank everybody on the systems team at Knewton. So Dave, Danny, Devin, John, Peter, Solon, and Tim, they were all really, really helpful, especially Dave and Peter in trying to help me get spun up on autoscaling as a problem and writing Leptoid. They were extremely helpful while I was freaking out and having minor panic attacks during the whole graphite cluster meltdown thing that happened, or things, because it happened more than once. But they were super, super patient while that happened, and I'm really, really appreciative of it, and I really appreciate it. So anyway, I'll go ahead and show you some stuff that, that we've done so far with respect to Leptoid. So the first thing we have is some of the instrumentation stuff that we've done. So like I said previously, we instrumented our Nginx proxy logs using Logster, which is a great open source library by Etsy for parsing logs. It's really convenient and straightforward. And we just submit all of that data to Graphite. So as a result, now we have utilization information for our production environment right here, if I could find the mouse. And this is utilization for each of our different services and applications in production over the last week or so. And you'll actually see some of the things I discussed during the presentation confirmed here in these charts. For example, 925, I believe, was a 920, whoops. Oh, I see. So 926 was Wednesday. But in general, you continually see this type of behavior every day around noontime. You'll actually see utilization shoot up for that magenta-looking line. Sorry for picking these colors that aren't too discrete. But the general idea is around noontime every day, our recommendation service sees a very, very high increase in utilization. And so that service in that scenario might actually be a good candidate for an increase in capacity. But conversely, that quickly drops off as we start to approach 2, 3 in the morning. You probably can't see that too well there. But the idea is that, conversely, we can confirm that utilization drops off for our recommendation service as the night rolls on. And so that's a good scenario for actually downscaling our recommendation hosts. And similarly, actually kind of embarrassingly, you see that utilization for a lot of our services and applications are really, really low, right? Most of them don't actually even exceed 0.1, maybe 0.2 at best. I'd argue that this is all excess capacity that we have right now in production. And so once Leptoid is finished, has passed any testing and staging, and we deploy it in production, I imagine that these lines all the way down here will actually move up a little more as we decrease their capacity because they have so much excess capacity. Let's see. And so this is our instrumentation in staging. In addition, this was all a little bit of work, and it was all pretty ad hoc. We had to actually write our own Nginx log scraper. But the general idea is that this solution worked for us. And aside from the graphite data storage solution and the instrumentation solution, whether you use StatsD or Coda-Hales metrics or something else, once you have these two things squared away, you can work with your data scientists and your capacity planners to figure out a good model. You can work with your engineers to figure out a good deployment system. And and you could talk to your pointy-haired bosses and figure out a good motivation for actually working on an autoscaling library. But this is what works for us, and I think that I hope at least that what worked for us ends up providing some lessons that may work for you guys. Otherwise, I'll be here to answer any questions. Thank you. Thanks for your time. You could find Leptoid up there on GitHub. Otherwise, that's my information. Thanks a lot. I appreciate it, guys. I'm sorry, you said that everything is based on, oh.
It sounds like a lot of the stuff that you have is based on, that you discussed is based on historical data and analysis of historical traffic.
Right.
So how do you deal with anomalies or events? Say a client comes out that has a bug and starts hammering your service. How does your scaling solution deal with that kind of stuff?
Yeah, that's actually a very good point. So he mentioned that right now the way Leptoid is designed, it actually looks at historical data more than anything else. And that's actually a valid point. I think that when you're performing some kind of time series analysis, you actually need a decent amount of historical data to try to identify those seasonal and cyclical components I talked about. When it comes to bugs in production or anything like that, we actually have automated unit testing that occurs when we push builds to production, or push builds to staging rather. And so that tends to catch some of the bugs. When it comes to actual bugs that make it to production, I haven't addressed that too much with respect to Leptoid, unfortunately. That's one of the things that we would definitely need to address, though. I agree.
So it wasn't really, so bugs was just an example, but I just meant, I mean, if you're relying on historical data, it's by definition stale the moment that you're using it, right? So even say that you have a service that starts to become very popular, that isn't necessarily a defect, but you would have to ramp up really quickly. So is there a way you could override the algorithm, or?
I actually see what you're saying now, right? So part of the historical data actually includes, data that's just passed recently. We actually, the algorithm actually, the model that we're using actually analyzes data at the minute level. And so historical data ends up being something like 5 minutes ago, 10 minutes ago, an hour ago. And so in addition to that, since we're working on solving education problems, we see pretty consistent behavior from students. So actually the main problem we have is at the outset of a semester, when you start to see a ton of people flood into our systems. We managed to address that okay this time around for fall 2012. But the idea is that as time continues, we can use some of the lessons we learned about kicking off the new semester for future semesters. And we can also use forecasts from our partners, like our textbook partners and our university partners. We can use their student usage forecasts to kind of inform how much capacity we need at the beginning of the semester. So there's no like hockey stick growth type stuff that we're experiencing, except for at the beginning of the semester, and we can work with our partners to try to figure out what load we're expecting at that point in time, and that helps us inform our initial capacity planning decisions at the beginning of any semester. Does that answer your question? Okay.
Hi. You mentioned that the only available statistical, single value decomp, another type of library for Python was rpy2. If you had to do this in another language and you could do it based on what stats library you wanted to use, are there other options that you'd prefer?
So that's actually a good question. There is actually stats models in Python which will solve this problem relatively soon. I actually talked to the library's author and I offered to contribute a little bit, but he's working on multiplicative decomposition right now. If I had to pick any language right now to do this in, it would, solely for its modeling facilities, I would probably use C or C++, but it's pretty obvious, right? The only other people really doing time series analysis, aside from capacity planners, are people in finance, and they're all writing their models in C and C++. I actually just went with Python because I found it to be the easiest way to get this library started from nothing up to what it is now. But from a pure modeling standpoint, C or C++ are probably the way to go. I can't think of anything else other than those two or Python that I would use. Great, guys. Thank you.